Oseland, graduate student studying weed science at the University of Missouri. I'm out here today in one of my research trials where we're attempting to evaluate yield loss in soybean following exposure to synthetic auxin herbicides such as 2,4-D and Dicamba with drones. When soybean are injured with synthetic auxin herbicides, there are several factors that can contribute to yield loss. These include the growth stage of the soybean at the time of exposure, the temperature or environmental conditions following exposure, and the rate or amount of the herbicide which the soybeans were exposed to. The growth stage of the soybean and the environmental conditions following exposure are two factors that we can measure. However, typically the amount of herbicide to which the soybeans were exposed to is unknown, and this is why predicting yield loss can be difficult. The sensors equipped on drones can provide a more quantitative and accurate assessment of soybean injury than what we can see visually. The goal of this research is to determine if drones could be a useful tool for predicting end-of-season yield loss in soybeans following exposure to certain herbicides. Human eyes can only see a narrow window of the light spectrum. Digital sensors, however, can be designed to detect a much larger segment of this same spectrum. The sensors used in our study are able to sense the same window as the human eye, plus a segment of the near-infrared spectrum. Having the ability to evaluate the near-infrared spectrum is important in this study, as plants strongly reflect near-infrared light. The amount of near-infrared light that plants reflect can fluctuate as they become diseased, stressed, or damaged. Many previous researchers that study plant reflection with sensors have developed vegetative indices, which are calculations that utilize different wavelengths to evaluate plant health. For example, NDVI, a very popular vegetative index, uses a simple calculation of near-infrared and red light. This vegetative index has been reported to be very sensitive to very small fluctuations in plant leaf area index, canopy, and structure. Over time, other researchers have found other indices that they reported were also sensitive to minor changes in plant greenness and structure. Therefore, we wanted to test some of these previously characterized vegetative indices to determine if they could be successful in quantifying soybean injury from synthetic auxin herbicides. Our study, performed for the past 2 years and again this year, has consisted of synthetic auxin susceptible soybean planted at 3 separate planting timings throughout the growing season. Applications of multiple sublethal rates of 2,4-D and Dicamba were applied to the soybeans when the 3 planting timings reached R2, R1, and V3 to allow for an evaluation of yield response differences between different growth stages. We also wanted to evaluate how soybean growth stage impacts the sensitivity of a variety of vegetative indices. The results of this study so far are displayed here. To better understand how we evaluate each vegetative index, let's take a closer look at one of these graphs. The black line indicates Dicamba treatments and the yellow line indicates 2,4-D treatments. The values on the x-axis consist of the percent reduction in the value of each vegetative index in the treated plots compared to the non-treated, and the y-axis is the percent yield reduction in the treated plots compared to the non-treated plots. We look at the R-squared of each treatment to determine the strength of the developed models, or in other words, the R-squared indicates our accuracy in predicting potential yield loss with that vegetative index. Therefore, with the Dicamba line on this graph, we can say with 86% confidence that a 1, 2, and 5% reduction in GNDVI values would equate to 15, 25, and 50% reductions in yield respectively. However, the models were not this accurate for each vegetative index. For example, on the same graph, we can only be 42% confident in the yield estimates following 2,4-D injury. Therefore, in this case, we will look through our other models for this growth stage and determine if any other vegetative indices were better at predicting yield loss following 2,4-D injury at the R2 growth stage. What we can see is that no vegetative index was very accurate at predicting yield loss at this growth stage. Therefore, in a real-world setting, we would only be able to accurately estimate yield loss following 2,4-D injury at the R1 growth stage or earlier. However, for Dicamba injury, there were many vegetative indices that provided a fairly accurate estimation of yield loss. GNDVI was the most accurate vegetative index for estimating yield loss following Dicamba exposure across all growth stages. The results of this study ultimately show that utilizing proper vegetative indices can result in mostly accurate soybean yield loss estimates following injury from 2,4-D and Dicamba. Future research will evaluate the time intervals after injury that result in most accurate yield estimates, as well as comparing visual injury estimates to the UAV sensors to determine if drones are truly a better predictor of yield loss.